Good day. In this presentation, I'm gonna talk about the stress intensification factor, which is the SIF, or as per Hexagon and most of the people they are mentioning as SIF. What is the function of the SIF? SIF is a safety factor which is multiplied by the stress to reduce the allowable stresses for the components, for special components. When we tried to create the software, there was a problem that we need to make a calculation or an experiment for every component. So they come up with the idea of the SIF. The SIF actually is related or number or factor coming from experiments for low cycling fatigue loads. It's come experimentally. P31.3 and P31.1 was working on experiments done by Merkel in 1940s, and we're still working on it up until now. But with P31.3 2020, the Appendix D had been deleted, and currently we are working and recommended by the ASME P31.3 to work with the ASME P31J. So stress intensification factor, it's a factor multiplied by the stresses to increase the stress of components to compare it by the allowable stresses. If we went to Caesar, we will find it coming like this. And later on this presentation, I will open Caesar and show it to you. If we go to the code, I'm getting this from the P31.3, and it has the same with P31.1. You will find that this is the equation for the flexibility of the thermal stresses calculation, and this is the equation for the sustained stress calculation. You can find that it comes with the axial stresses, the bending stresses, and the torsional stresses. All of them are calculating by the stress intensification factor, which is, you will find it by the IA, IT, and here we have IO, IA, II, and IO. IA is the axial stress intensification factor. IT is the torsional stress intensification factor. And for when we are calculating the bending stresses, we have in-plane stress intensification factor and out-of-plane stress intensification factor. I will explain this later. When we go to calculate the sustained stresses, you will find that we have capital I and capital IO, which is the sustained in-plane moment index. We mentioned it as SSI. And for the torsional, we have the IT. And for the axial, we have, sorry, for the longitudinal, we have the IA. And when we look on the explanation of this, you will find that the code mentioned if we don't have more applicable data, we should use for the IO 0.57 the IO. And for the II, we should have the 0.57 if we don't have applicable data. For the torsional, we consider it as 1. For the axial, we consider it as 1. Of course, this in the absence of more applicable data. And by the way, it's more applicable data is mentioned 10 times in the code. This is show how much this stress intensifications are not that accurate. And this is why we are going to use the B31.J or even the FEA these days. And I will explain this later in the presentation. I'm just showing you how much important is the stress intensification factor, the SIF. Okay, what is the difference between the SIF and the SSI, or sustained stress index? SIF, actually, it's working with the number of cycles, with the fatigue load. This is why it's using for the thermal analysis of the flexibility stresses based on, as the code mentioned it. So SIF is the stress amplitude to failure of the gross path weld in number of cycle, in certain number of cycle, divided by the stress amplitude to the failure of the component in the number of cycle. While the SSI is related to the collapse or the excessive distortion of energy inside the material. This is why the equation for it is equal to the collapse of the straight pipe divided by the collapse of the part. We are using in the SSI twice elastic slope method based on nuclear power planets, which has been issued in 1981. If we are to get it short, if the dt is much smaller than 50, we are using the SSI as 0.75 SIF. And we take the I equal to 0.75 I. If it's not, I will show you how we can later. I will show you how we get it. Although the software is calculating, but these days we are using the FEA if we need it, and I'll show you when we will need it. If we went to the Appendix D, which is already deleted, by the way, in the edition of 2020, but I should show it to you in case you use it. This is the Appendix D for the P31.3, and this is the Appendix D for P31.1, which still exists. It's not deleted yet. Okay. I copied this from these two paragraphs from the P31.3 just to show that he's mentioning that the ASME P31.J, we can read it. Flexibility and stress intensification factor, ASME P31 paragraph 319.3.6. The flexibility factor K, which is, you will find it here, this one, and the stress intensification factor I, which is this one, shall not be less than unity in the absence of more direct applicable data, as I mentioned. The flexibility factor K and the stress intensification factor I shown in the ASME P31J shall be used for the flexibility calculation. Described in the paragraph 319.4, flexibility factors and stress intensification factors for branch connection are defined for in-plane, out-plane, and torsion moments on both the run and the branch legs. This is the paragraph I had copied from ASME P31.3. And this is why it's mentioned that we are using P31J, because this table had been deleted in 2020 edition. But in case you have the older version, I decided to show it to you just not to be confused. Also, if we compare between the P31.1 and P31.3, we'll find that P31.1 does not consider the outplane and in-plane stress intensification factor. It's only the P31.1 only mention one I, use one I, while in the P31.3 we have the out of plane stress intensification factor and in of plane stress intensification factor, or SIF. Okay, what is the meaning? Many people ask me, what is the meaning of the out of plane and in of plane? If you went to the P31.3, you will find these two drawings, which is self-explanatory. if you have an elbow or an T, you'll find that the bending moment, this is the bending moment for the out of plane, and this is the bending moment for the in plane. Same for every point or exit point in the pipe. Which means if we throw this T on the floor, the force that will make this T rotate on its axis is the out of plane. The force that will keep it on the floor is the in plane. Same here in the elbow. If you do the same, we have this is the torsional moment. This is the bending moment, the out of plane bending moment. This is the in plane bending moment. Okay. What is the ASME B31J? In 2008, the Pressure Piping Technical Committee on Mechanical Design, which is the MDC, decided to issue a new standard and create a new, which was in that time recommending just extra tests for calculating the SIF. But by 2017, the committee had issued the code, the ASME B31J, with tables for calculating and equations for calculating the SIF and the SSI clearly. Okay, what is the typical tests inside the B31J? Is the PRAS test, the SIF test, the K-factor test, and the strain load test. This is what was required in 2018. If we go now, this is a copy or a screenshot for a table, the welded T table in the B31J. Of course, and this is a screenshot for the table of P31-3. You can find here he's calculating the flexibility factor K in plane, out of plane, and torsion. In the old calculation for the P31.3, we don't consider the torsion and the axial SIFs. Here, the new code is considering the torsion SIFs. And this is the calculation for the branch. This is how to calculate the SIF in plane, out of plane. This is for the header, and this is for the branch. Of course, here you can find it. It's much easier, but it's not accurate. Actually, in some pieces it's over conservative, and in some cases it's not conservative, and there is a mixing area between them. This is a comparison, a small comparison, that as you can see, the P31.3, the appendix, is coming in between the calculation of the P31J in 2017. But when we make the comparisons, we found out that the P31.3 Appendix D is over conservative when D over D, which is the branch diameter divided the header diameter, is less than 1. It's over conservative. And when we found that the appendix D is non-conservative when D over T is bigger than 50, when D over D is between 0.5 and 0.9, when T over T is less than 1. This is the cases that when the appendix D is conservative and when the appendix D is non-conservative. Okay, I decided to take an example and show you how we make a calculation for the thermal stresses. And also I will show to you on the scissor right after this explanation. If we have a pipe, 24-inch pipe with a branch 14-inch, the pressure inside this pipe is 14 bar. This is the diameter, the outside diameter. This is the inside diameter when I subtract the thickness. First, what we will do, we will calculate the area for the outside diameter, and then we calculate the area for the inside diameter. And to get the diameter, the area of the pipe, we will subtract the inside area from the outside area, and we give you this number. Then we will calculate the axial force by multiplying the pressure times the area inside area. So we can calculate the inside force, which is the hoop force, and we get this number. After we calculate the axial stresses for the pipe, which is the axial force divided by the area, cross-section area of the pipe, and we will get this number. Of course, I'm getting the numbers big to reduce the error as much as I can. After, to get the stress, the axial stress on this T, on this T, because this is a T connection, welded T connection, we will multiply the IA, and based on this, as you can see, the IA is equal to the IO, which is the SIF, outside SIF, or out of plane SIF. So here we consider the out of plane SIF for the IA and multiply it with the axial stresses, or the axial stresses here, and we get this number. How we can calculate on the allowable stress based on the equation in the P31.3, and I consider it for ambient temperature. In case of that you have any other temperature, then SH will make a difference, and you can extract this data from table A in P31 ASME P31.3, and or if you are using ASME P31.1, you should use the table in the Appendix A in ASME P31.1. So the equation of the allowable is equal to the factor of cycling factor times to 1.25 cold stresses plus 0.25 hot stresses. And when we calculate it based on this, it will be equal to this is the SA, and if we will divide the axial stresses by the allowable stresses, we will get the the ratio between these two, and this is how the software even do this. Okay, right now let's go and let me show you my example. This is my example. This is a 24-inch pipe, and this is a 14-inch pipe, and we consider water here for a carbon steel, and temperature 21 and pressure 14 bar. Okay, we here consider the SIF, and we mention its welding. If you need to know what exactly the SIF for the P31.3, you can easily write here. If we open here, this is note 20, so what you do, they just mention 20. He will get you the header SIF and the branch SIF that is mentioned in plan and out of plan, if you want to know exactly what he's doing. By the way, if you want to show, let me show you something. If we change it to P31.3 and go to the SIF, you will find that he close everything except the in plane, because P31.1 does not consider the in-plane and out-plane and torsion. But if we go back to P31.3, you'll find out that he's opening the in-plane, out-of-plane, the torsion, and the axial. Okay, we can run this. And you can find the stresses here for the thermal. Of course, you will find it different from mine, because here the calculation metrics that is been using is somehow will be different from even the decimals that he's using. This is why there is a difference, but we are both using the same method. And here's the axial force, the bending moment, the torsional moment, the SIF in plane, the SIF out of plane. The torsion SIF is, you see, it's considered one, and this is wrong. Sometimes I'm not saying it's wrong, but sometimes it's not conservative. And this is for the axial, it will also consider it one. This is based on this, as it's mentioned, that it should be considered one, i.e. for elbows, pipes, and miters in case of the absence of more applicable data. Same, you will find it here in this paragraph. Okay, let's go back. And this is how we calculate the more or less the output for stresses based on the P31.3. Okay, if we open the PRG, which is polling group, study and make his calculations, make his experiments, and come to us with the FEA tools. Let's see, we will press here to open it. Let's consider pipe, our case, which is standard pipe. This one, copy, and we control volume here. Go back here. And we have as you can see, I just make an input for the diameter for the round pipe, which is the header, and the branch pipe, and press here, compute the SI. As you can see, this is for the ASME B31J 2017, and this for the welded T. This is the in plane for branch, out plane for the branch, torsional, SEF for the header, in plane, SEF for the header, out plane, SEF for the header torsional, the flexibility factor, in plane for the branches, out of plane, torsion, and same for the header. This is all should be calculated by the P31J. But if we go back to the P31.3, you found that there is no torsional calculation. It's being considered one. And you will find that the difference between the out of plane is huge, 4.2 to 3.4. This is a difference, which is make higher stresses. Same, you will find it with the in plane for the branch. Also, you will find you can recognize that it's been considered 1 for the SIF outside plane, while it's considered 4.22 for the out of plane branches. Same, it's the great difference between these two numbers, which give a great flexibility. Also, you can find here it's near to the nuclear code. This numbers is much near to the nuclear code. And here, this is the PRG stiffness calculation. Also, you can find that d over d, t over t, d over t, d over t. And you can calculate the sustained stress index here. As you can see, the program give you a recommendation for the P31J 2015, and this is the way that been calculated by the old ASME P31.3. But P31J give you some conditions to apply this one. If you need just to use the one that is recommended, the P31J, and if you compare it, you'll find a great difference also between this and this. In 1.72, we are talking about 2.23, 2.5, and 1.8. You'll find the great differences. And by the way, if D over T is between 30 to 40 for the fabricated SIF, the fabricated T, SIF, it's getting higher. And stress accuracy in the time is suffering from the high stresses. Also, the SSI will be suffering the same from the high stresses. This is why the SSI should not always be a fixed multiplication. Also, you will find the problem with the torsion, because in the old code we don't consider the torsion. Here we consider the torsion. If you see, the P31.3 is not considering the torsion. And if we take it like, let's make a comparison. If we are using the P31.3 SIFs and the P31J SIFs, you'll find that we are talking about, sorry, not SIFs, the SSI, and I'm sorry, the SSI. You'll find that we are talking about 3.1667, and here we are talking about 2.563, which is a great difference. And this is always happening. This is the main difference you'll find always in the outside SSI in the branch. Okay. Also, the FE tools have a great tool for stress evaluation. We can use it if we go back to our calculation and we open the global forces. Here we can find our T is on node 20, so we have the in plane and the out of plane. The out of plane is here, this one, the forces out of plane, and here is the in plane. So what we will do, that we will enter the data here. Number of cycles, we have the problem here that this evaluation is only working with the English unit. So we need to change this to English unit. Let me show you how we can change this to English unit. We go here and we go to utility, change model unit, and we can tell it English unit, press OK. Sorry, there's an error. Okay, done. Go back here, open. you will find that all of the program had been changed to English unit. Let's run it again. And the output, why it's not changed to English unit? It should be changed to English unit. Okay. So first we need to enter the pressure that we can check the pressure here. PSI. So we have this. Put it here. He said the in-plane moment. We go open the results again. And go to global and thermal operate, which is the operation case. And open here. He wants the in-plane moment. If you remember the one that we opened it in the this one, we need it for the T. We need the in-plane. In this case, the in-plane moment is the acting on the direction of in this case we will have the in-plane which is acting in this direction, which mean acting like this. Okay. And by the way, we need to change this option to 7 cycles only. Okay, because we are using 7 cycles only. The out of plane, if we go back to check the out of plane, here is the one affecting the pipe, which is this one. Also, we need the torsional case. Here, you see the torsional is important, although it's not shown here. It's considered here by 1. This is why it's important to use the FE SIF. And the axial load, also we can use the axial load here. Now, we have as you can see, this is our points. We're still under the allowables. But let's consider this is the PPV. This is the conference that had been done in 2007. And this is the ASME smooth bar for the section 8. This is the mark calculation which had been done in 1940s. And this is the P31.3 as you can see, they are both going all together because P31.3 is still using the Merkle study, while this is the Section 8 and this is the conference, PPV conference 2007. This is a good way to show the graph for this calculation, which is done by the FEA tools. And also you can tabulate it and get your data. This was a brief explanation for the FE tool. And by the way, I was promising you to know when exactly should we use the FE tools. The FE tools give a very helpful tool here in ASME, in Caesar, a critical evaluation, where you can put the data and the FE will give you the if we do the example, our example, the D over T was 63, the DD was 0.576, number of cycles we are using 7,000 cycle. No need for it if we don't have the data. Our temperature was 21. Okay, our temperature here. I'm not good with the units, so I'm depending on the software mainly for this unit transfers. 6. If you want to change it, by the way, to metric, I forgot that we can use the metrics. And here he mentioned to you if the system connected to rotating equipment, which is pumping or compressor, if the pipes is not carbon steel, if you are buying from a low fabricator, if the D over T is less than 0.7, here we have 0.5, so we are safe. Piping is the piping system considered tight. If the routing of the pipe is tight, you can use this. If there is OLED, which is used on the system. Also, he give you the option to use the P31.1 or P31.3 or even the pipeline type code, which is the P31.4 or P31.8. Also here, he give you in the thermal condition, if the SE is over than 0.7, 0.8 SA, and this is, you can find it in the ratios that we was using in the stress report, and we was lower than the 0.2, the SA, I think, and we was here, I think, and press the evaluation. He will give you this card. This card is very helpful if you need it, because he mentioned clearly how you can read the evaluation. This part is very important. He tell you that if it is less than 5, then the system is not sensitive to the SIF or the flexibility factor. If it is between 5 to 10, then the system has at least a single character that may result a sensitive SIF, which is still not that important. If the 10 to 15, there is a multiple properties of this system that could result in a sensitive of the SIF. If it is above 15, you should use the FE tools, the FEA tools for these two cases. And by the way, I will explain to you more that in the next not the next session, the next few presentations, I will tell you how we will use this FEA tools translator. It's easy, we can, but I need to explain it more. I will just show you a small demonstration. We can open it here. Mention I need this one. Open. He will open it. Is the currently default, and then you'll start to make the converter. He asks you if you want to use the finite element or the ASME BJ or translate it to SIF for the support. You will use this one. By the way, this part is important when you are using the FEA, that we don't use heavy pipes. Heavy pipe is the old pipes. You can read it here even. I mentioned to you that light pipe is the type. It is known that light pipe is the one that we are using right now that is compatible with the ASME B31J and the B31.3 is the medium. Heavy is this old pipes, okay? And this different type, but mainly we usually use the P31, the medium, if we are using for a new planet. So you need to change it to medium and go back to global, or even you in my case it's not important because I'm not overstressed. But if you have overstress, you will need to use the FE, because the FE give more accurate results from than the ASME P31J. And then we press convert and keep the program working until it finished. When it's finished, it will give you a report, and you can make a comparison here. You can open it from here. You will find that he already create a folder for you with input folder for you with the new output, and you can open it here. And if we come, okay, I opened for old one, but anyway, for another example, if you will come to the SIF, you will find that he already input some SIFs. Let's go back, input, change the folder for each folder. Sorry guys for this mistake, and you'll make the conversion. You'll find that he already input the SIFs and the SSI index for the pipe based on the P31J. We can run this calculation, but we need first to close this. Okay, twice. Sorry. You can find that the output had been greatly changed based on the new index and the new SAFs that had been used. Here for the thermals, the SAFs, if you remember, that I said that the SAFs for the thermal and the SSI index is for the sustain, which means if we go here, you will find the different numbers which compared to the index. Okay. In the end of this presentation, I hope this was helpful for you. This information was helpful, and I explained the SIF in an easy way. If you got any question, please communicate with me. Send me on LinkedIn, give me a comment on my page. I'll be happy to hear from you back. Thank you, and please, if you like this video, give me a thumb and come subscribe to my channel and press the ring bell to get my new videos. Thank you.